Good morning, everybody. I'm Brian Greene, co-founder of the festival with Tracy Day, and as I was about to come on the podium, I felt something odd in my pocket. This is not a plant, and it's my little daughter's little monkey. So I'll just put it over here for good luck for everybody. So last night, we had 3,300 students and teachers and parents up at the United Palace Theater learning about general relativity and black holes during this program, Icarus at the Edge of Time. Really thrilling just to see these kids light up when they learn about these ideas of science, which is what this festival is all about. But our proudest moment actually was yesterday. I didn't see it firsthand, but on Jeopardy, one of the categories was World Science Festival yesterday. Look at that. So thank you, of course, for joining us this morning for the announcement of the 2012 Kavli Prizes, which is a partnership between the Norwegian Academy of Science and Letters, the Kavli Foundation, and the Norwegian Ministry of Education and Research. And as I think all of you know, these prestigious prizes recognize scientists for major advances in three areas: astrophysics, nanoscience, and neuroscience. And the Kavli Prize recipients are chosen every 2 years biennially by committees of distinguished international scientists. And we are very proud to have presented the prize announcement since their inception back in 2008. This is the third installment. And I now would like to just spend a quick moment thanking the festival sponsors who make really all of this possible. The Simons Foundation, the Alfred P. Sloan Foundation, the John Templeton Foundation, our great friend and friend of the festival, Ann Ziff, Con Edison, and of course especially the Kavli Foundation. We're grateful as well to New York University, John Sexton, David McLaughlin, Lynn Brown for giving us the opportunity to come together in this really wonderful room, this great new building. And we as well have some very distinguished guests in the audience, Nobel laureates, heads of universities, representatives from Norway, United States, as well as from other countries. And I just want to quickly acknowledge a few of the guests that are here. Of course, Fred Kavli, who I have known back since 2003. You can please stand, deserve a round of applause. A brilliant inventor, entrepreneur, and now one of the world's greatest philanthropists of science. He has had a fantastic, profound impact on science already, and it will continue far into the future. Robert Cohen, president of the Kavli Foundation as well. Owen Andersen, Secretary General of the Norwegian Academy of Science and Letters. And we are also delighted that this morning's program will be moderated by Richard Besser, ABC News Chief Health and Medical Editor. Dr. Besser is the former acting director of the American Centers for Disease Control and Prevention. And it is now my honor to introduce the director of the White House Office of Science and Technology and Policy, President Barack Obama's senior science and technology advisor, John Holdren. Since joining the administration in 2009, he has focused on ensuring that federal policies are supported by sound science while working to create science and technology jobs, strengthen science, engineering, and math education, which of course is so incredibly vital, reduce reliance on energy imports, mitigate climate change, and support the application of biomedical science and information technology to help all Americans live healthy and connected lives. He's an aerospace engineer and plasma physicist by training, and one of the nation's foremost experts on energy technology, nuclear arms control, and non-proliferation, and global environmental change. Please join me in making a warm welcome to Dr. John Holdren.
Well, thank you, Brian, for that kind introduction, and thank all of you. I have to say that picture of me is all too realistic, but nothing to be done about that. A very good morning to everybody. This is really an exciting day. As you've heard already, I think in a little less than 30 minutes, we will be going live to Norway to hear the announcement of this year's Kavli Awards. And in just 4 years, I have to say those awards have taken on a, shall we say, Nobel cachet. I don't want to insert myself into a Scandinavian battle of the benefactors. Everybody still loves the Nobel prizes, But I know that the American journalists in this room will agree that Fred got one thing right when he invented these awards, and that's the timing. Because the Kavli Award, as you can see, gets announced at this very civilized hour, which means that reporters don't have to wake up at 5 in the morning, which is when the Swedish website unveils its winners. So that's a great benefit. Well, we've had a nice breakfast. I hope everybody is well-nourished and looking forward to this really wonderful expression of support we all get to participate in for an exceedingly worthy slate of scientists and innovators. Innovation, of course, is at the core of what we're celebrating here today and over the next few days, not only with these awards, but in the many venues and events comprising the World Science Festival. And if some of you are wondering why, of all things, you've got a government official standing in front of you at an event dedicated to innovation and creativity and thinking outside the box, well, that is the story I want to tell. Because if there's one idea I want you to walk away with from this opening session this morning, it's that of all places, Washington, D.C., the federal government under President Obama, has become a crucible where new and creative policies are being forged specifically to support breakthrough science, to enable novel technology, and to catalyze paradigm-shifting innovation. And not just because those activities are so stimulating and exciting intellectually, but because they are the essential underpinnings of economic growth, of improved health care, of job creation, of sustainable energy and food supply, and of national and homeland security. This focus on innovation is new in the government. Traditionally, when people, and especially scientists, have thought about what the federal government does for science, the one answer that's come to mind is we fund it. We hand out money to scientists. And that's true. We do give grants. We give contracts. We've basically said, here's some money. We're counting on you that it will pay off. And that's not a bad system. It's worked pretty well. I think we're all familiar with the value of blue skies, unfettered support for basic research, and we still do that, and the President remains committed to it. In his first major talk about science in his administration, which is at the annual meeting of the National Academy of Sciences just a couple months after his inauguration, he spent about 60% of the time talking about the value of fundamental research, of basic research, and not, as some might have expected, about all the important applications. But we have, in fact, focused on the applications as well, and we have tried to engineer a new set of processes specifically designed to spur creative solutions to technical challenges and to get more bang for the research buck, which is obviously a good thing to do given that there are fewer and fewer bucks to go around these days. Let me give you some examples of this. First, consider what went on just last week as a commercial rocket made by an American company named SpaceX launched from the Kennedy Space Center, successfully placed into orbit the cargo capsule it was carrying, which in turn extended its solar panels, navigated to within 30 feet of the International Space Station, some 250 miles above the Earth, while both were moving in orbit at 5 miles a second, and then berthed with the space station so astronauts could spend Memorial Day unloading the 1,100 pounds of supplies that that commercial rocket and capsule had carried up there. This was the first time an American spacecraft had gone to the station since we retired the space shuttle last year. And an even bigger first, the rocket and capsule were not just made by, but owned by a private company. This represents an entirely new model for the American space program, one initiated by this administration, and one that, despite the hand-wringing of naysayers who said it would never work, now promises to change forever the nature of U.S. space exploration and human spaceflight. Because by handing over to the private sector the work of ferrying supplies to the space station, and before long ferrying astronauts as well, we're leaving NASA more free to focus on developing innovative solutions to even bigger challenges, so we can pursue bolder goals like landing on an asteroid, landing on a moon of Mars, and ultimately landing on Mars itself. This is a much better deal for the nation than having government continuing to do what the private sector can now do more efficiently and less expensively, and creating, by the way, new industries and jobs as it does so. Of course, SpaceX is not doing this entirely on its own. As with all the examples I want to mention this morning, it's working hand in hand with the federal government in a public-private partnership that ensures a solid blend of private entrepreneurial ambition and public responsibility. In this case, NASA engineers worked seamlessly alongside SpaceX engineers and showed that it's possible to pursue this very complicated, brutally unforgiving, and inevitably expensive endeavor far more efficiently and with less taxpayer expense than the old government model. And at least one other private venture, I should say, is close on SpaceX's heels. We're getting the benefits of competition in this domain, and it's going to continue to lower costs and increase efficiency. Another thing we're doing differently in this administration, policy-wise, to promote innovation, is our major push to add challenges and prizes to the portfolio of strategies used by the federal government to get things done. As I mentioned earlier, the conventional model for supporting scientific efforts is for the government to give a grant and hope that the grantee accomplishes what she or he promised. But there's another way, a way that in the right circumstances and for certain kinds of challenges can be far more cost-effective because it taps normally overlooked sources of innovation. That method is to offer a reward for the first person or team to solve a specific challenge. Prizes like these have a long history, but they've mostly been used in the private sector. Consider the Orteig Prize that inspired Charles Lindbergh to fly solo across the Atlantic, or last year's Automotive X Prize that awarded a total of $10 million in prizes to 3 teams that built cars able to get the equivalent of 100 miles per gallon or more. Well, why prizes? For one thing, unlike grant givers, prize sponsors don't pay a penny unless someone actually solves the problem. For another, taken together and sometimes even individually, competitors for prizes often spend far more on their efforts than the value of the prize purse itself, each competitor inspired by the prospect of winning bragging rights. In the case of the Automotive X competition, $10 million in prizes, $100 million was invested by the competitors to develop these 100-mile-per-gallon vehicles. And consider as well that this approach often attracts citizen problem solvers who are not among the usual suspects in the grant application world. In one typical example, an intractable problem that NASA posted relating to radiation protection in space was solved by a retired radio engineer living in New Hampshire. Despite these and other benefits of the prize and challenge approach, it has been underused by the federal government until now because, in part, many agencies didn't have the legal authority to use their appropriated funds in this way. And in part, it hasn't been done very much because the agencies simply didn't have any experience with this model. We've changed that. First, the President signed an executive order calling upon agencies to start considering prizes as realistic options. Then the Office of Management and Budget followed up with guidance on why it pays and how to do it. We got language in the America Competes Act authorizing all departments and agencies, congressional authorization. All departments and agencies can now use their funds for prizes and challenges. And my office, in conjunction with private sector actors with lots of experience running prize challenges, held a workshop where hundreds of federal officials got to train in the use of this approach to problem solving. And we launched challenge.gov, which is a one-stop shop where solvers around the country and the world can see what problems the government has posted that have prizes associated with them. Today, this has become a significant part of the American research portfolio. We've already had some remarkable success stories, from creative digital games that teach kids the basis of nutrition. That was at the request of the U.S. Department of Agriculture, to an inexpensive device for safely stopping uncooperative fleeing vehicles. This was done at the request of the Air Force Research Laboratory. So this is another way that the government has been redesigning policy specifically to encourage greater innovation and to be a force for creative problem solving. Third example has to do with data. One thing the federal government is very good at is generating data. Every agency has scads of data, but too much of this information is effectively unusable. It's printed on paper, or digitally frozen as PDFs, or maybe it's even machine readable in an open source format, but buried so deeply in some godforsaken digital burial ground that nobody knows how to find it or even that it exists. It's a huge wasted resource, and we're changing that. Early in the administration, we committed to making more federal data available, and we've done so in a big way already through portals like data.gov, which today has about 400,000 government data sets available, a number that has been growing every day. But that is not all we have done. Just 2 weeks ago, the U.S. Chief Technology Officer, CTO, and Chief Information Officer, CIO, together made a presentation here in New York at TechCrunch Disrupt, which is a big and very ungovernmenty tech venue, where they unveiled a number of exciting initiatives aimed at turning government data into useful and economically stimulating information. They announced an open data initiative that will make much more federal data available so that private third-party innovators can develop apps that turn those data into useful information for consumers. They also announced that the federal government is going to start moving its data and applications onto mobile platforms, since more and more people are using mobile devices like phones and tablets as their primary means of getting information from the web. And they announced a Presidential Innovation Fellows Program. Again, this is just 2 weeks ago, Presidential Innovation Fellows Program that will bring creative entrepreneurial innovators from the private sector to work closely with federal employees for 6-month tours of duty to help feds break through longstanding bottlenecks in areas like health, energy, public safety, and education. Those endeavors are building on ones already working, including the so-called Blue Button Initiative, which now allows millions of veterans, Medicare recipients, and others to simply click an online blue button to securely download their own medical records. And the Green Button Initiative, which allows millions of consumers to download, with the click of a button, their energy use information so they can look at their use patterns, compare with friends, choose more cost-effective rate plans, and even conduct energy audits on themselves to find ways to cut energy use and save money. These endeavors are all happening because the administration brought private sector representatives to the table, helped hammer out common technical standards that all agreed to use, and then got out of the way and let the private sector do what it does best, innovate around the data and provide products and services of value to consumers. I finally want to mention one last realm where this administration has been working to strengthen innovation, and that is in the domain of science, technology, engineering, and mathematics, that is STEM education. The President has often said that he thinks the single most important thing we can do for the future of our country is to lift our game in STEM education. Our educational system has been, let us say, sporadic in the adequacy of its training of the next generation of makers and doers in STEM domains. But we're changing that, and we're changing it in a big way. We have taken on in my office a major effort to identify the hundreds of STEM education programs funded by various agencies with the aim of eliminating wasteful or ineffective programs and scaling up the ones for which there's good evidence that they actually work. But beyond that, and in keeping with my theme this morning of engaging the private sector as a partner, we've launched a number of initiatives that have brought corporations, universities, philanthropies, and others into the cause of raising the bar on STEM education. Programs like Change the Equation, which has recruited more than 100 chief executive officers of major high-tech corporations to do their part to fix up classroom laboratories and enhance STEM teaching. Or the President's Educate to Innovate program, which has generated $750 million in donations and in-kind contributions from private sector and philanthropic sources to improve STEM teaching, to send real scientists, mathematicians, and engineers into classrooms to speak to students, to work with teachers upgrading the in-class hands-on experiences in these domains, and to serve as role models, demonstrating to kids the exciting careers that are available in these domains. What I have been describing this morning, with the benefit of talking fast, and I apologize, but I'm watching my watch, is just a sample of the ways in which those of us working in the Obama administration have been working to try to make sure that this nation stays #1 in science, engineering, and innovation. And there's more. We're doing a lot to enhance advanced manufacturing in this country, a fast-growing part of the global economy that the United States intends to stay on top of. We're growing jobs in these areas, in part by working with community colleges to coordinate curricula to match local workforce needs in manufacturing and other growth areas. And of course, we're working very hard in the domain of energy and environment, among other things, to minimize future changes in global climate and to adapt to changes that we can't avoid. So I want to commend Brian and Tracy for inventing the World Science Festival and the role that that's had in opening the eyes of so many New Yorkers and others to the beauty and exuberance inherent in science and technology. I want to thank Fred Kavli for his incredible leadership in this domain, spectacularly productive innovator himself who has applied so much of the resources gained by that to the support of science around the world. And I hope all of you come away from this event this morning knowing that we in Washington are just as excited by the beauty and the potential of science and engineering and math, and just as committed to strengthening science, technology, and innovation for years and decades to come as the great leaders who have made this event possible and the Kavli Prizes possible. With that, I think we have a few minutes for Rich to ask some questions before we jump to Oslo. So I'm going to be joined up here by Richard Besser, and we will proceed.
Well, thanks very much, John. It's a real honor to be here for the Kavli Award ceremony, and it's an honor to be able to ask you a couple questions about science. One of the topics you touched on was the importance of unleashing scientific imagination and creativity. And one of the ways we had interacted years ago was around the pandemic flu in 2009. Recently, there's been some discussion in the media and around the world about types of research that take place and the issue of open science. In particular, the question was around dual-use research going on in laboratories to try and understand flu transmission, to prevent the next pandemic, or to be able to respond to it faster. And some of the questions raised were, what do you do when the research going on, the creative work of scientists, has the potential to be used not just for good, but for harm? How, as a federal government, do you oversee that and decide whether research should be totally open?
Well, first of all, Rich, I would say that research in a great many domains has potential both for good and for bad. And so this is not a new problem in a sense. We've long had the problem of how to compare risks and benefits of advances in knowledge and what we can do to make sure that we maximize the benefits and minimize the risks. And that still is the basis of how the government is approaching these matters today. In the case of the research on the transmissibility of particular influenza bugs, the process that the government goes through to ensure that we try to maximize the benefits and minimize the risks includes, of course, review of applications for federal support as to that balance, to make sure that research that the government supports has a bigger potential for good than potential for misuse or accident.
Right.
We have, in the specific case of research on, in the biological domain, we have the National Science Advisory Board on Biosafety, the NSABB, which advises the NIH and the Department of Health and Human Services on issues in this domain, and was very much engaged in the recent controversies around H5N1 bird flu research. And we have an interagency policy committee with representatives of all the relevant agencies that has, in fact, in response to the H5N1 issue, crafted a new policy to upgrade still further the efforts that the government makes to ensure we get the maximum benefit and the minimum danger. And that includes, for example, specifying what kinds of biological containment is required in the facilities that undertake this kind of research. But just to be very clear, in the particular case of this flu research, there is great benefit, as you know, given your background in the biomedical field, there's great benefit in understanding what these bugs can do and how we can modify our surveillance programs to detect dangerous developments in time to develop countermeasures, in time to develop new vaccines and therapies. And on the other hand, you have to make sure that what you have done does not provide a recipe for terrorists or other evildoers from using that information to deliberately develop biological weapons. It's a challenging domain, but I think we're getting on top of it.
You talked about the importance of the STEM work that's going on, and I want to ask you a question related to that. Now, as a science communicator in my new role, I find it quite challenging sometimes to explain scientific concepts. And over the past year, there's been a lot of pushback from the public as the government has issued science-based recommendations for a number of conditions. Breast cancer screening, prostate cancer screening, cervical cancer screening. And these are based on analysis of the best available science. What is the government doing to work in the area of scientific literacy and in the area of trying to translate science to a public that has a very low level of scientific literacy?
You know, one of the points that the president makes when he talks about the importance of raising our game in STEM education is we actually need to do that for three reasons. Of course, we want to educate and train the next generation of Kavli Prize winners and winners of national medals of science and so on. But we also need it to get the technology-savvy workforce that the industries of the 21st century are going to require. And we need it to get the science-savvy citizenry, and this is your point, the science-savvy citizenry that a functioning democracy requires in an era when more and more of the policy issues in front of voters and in front of our decision makers have science and technology content. And in that last domain, of course, improving STEM education is a long-term project and is not going to yield dramatic results in public literacy and science overnight. But it's extremely important that we make the investments and create the initiatives to get going now. And at the same time, we need to work harder on educating the folks who long since had their formal education in school by the kinds of things you do in the media, the kinds of things that we as practicing scientists, engineers, and science and technology policymakers do in reaching out to wide audiences. I mean, I give a tremendous number of talks, the other scientists in the government giving a tremendous number of talks, appearances in media and so on, trying to explain the most crucial issues at the boundaries of science, engineering, technology, and public policy to wider audiences. We can't just wait to improve K through 12 STEM education and college STEM education. We need to do that, but we also need to get better at telling stories and explaining things in ways that intelligent adults, of which we have fortunately a lot in this country, and intelligent kids. And by the way, they're getting more intelligent all the time, as you can tell from the quality of the projects that are winning the science fairs and engineering competitions or robotics competitions around the country. But we need to do all of the above. And the most important single thing, I think, for those of us who are out trying to do that is getting better at telling stories that really bring science and engineering and innovation home. I mean, I'll give you an example. A lot of us talk about how more than 50% of the economic growth in the last 50 years has come from science, technology, and innovation. And people's eyes glaze over. But if you say an NSF grant to 2 Stanford students who happen to be named Larry Page and Sergey Brin led to the creation of a company that employs 20,000 people and generates over $60 billion a year in revenue, people get it. A story that is specific about how investments in creativity pay off in real terms. That's the kind of storytelling that we all have to get better at doing.
We were speaking earlier, and yesterday I had the opportunity to do a story on the new Intel Science Prize winner, a 15-year-old boy who's using nanotechnology to try and solve some of the biggest issues. And I think your point of looking for science heroes and the contribution of something like World Science Festival for being able to do that is very important, because this little boy said, when I asked him, who are your heroes as a child? Mm-hmm. He said, well, since I was 6, I was looking at the previous the Intel Science winners, dreaming that one day I would be in that book. And you know, my son knows all the baseball player heroes, but making science cool is something that it sounds like you're working to do.
We are working to do that, and President Obama is very excited about this whole domain. We've had 2 White House science fairs in which the president has met with the winners of 40 different science, engineering, robotics competitions around the country. And each time we have one of those White House science fairs, you know, the president is down on the floor with the robots, he's firing the marshmallow cannon, he's talking to the kids who developed new cancer therapies using nanotechnology. And when we leave those events, inevitably the president says to me, you know, that's the most fun I've had in months. But of course that's also a commentary on what else he has to do, but still.
Well, the impact of that is I'm sure, incredible. And it's now time to look at who some of the new science heroes are. Some of those people that hopefully the next generation will be trying to emulate. And we're going to turn to Oslo for our big moment, where my colleague Adam Rutherford of BBC and Nature is going to moderate the 2012 Kavli Prize announcement, live from the Norwegian Academy of Science and Letters. Are you with us, Adam?
Hello, and welcome to the 2012 Kavli Prize announcements. Welcome to the audience here in Oslo at the Norwegian Academy of Science and Letters, and also to our friends at the World Science Festival. They're watching live in New York, hosted by Richard Besser, ABC News' chief health and medical editor, along with many distinguished guests, including the White House science advisor, John Holdren, and previous winner, Tom Jessell, who, although he doesn't know who I am, his research heavily influenced my own research. My name is Adam Rutherford, and it's my pleasure to be the moderator for today's announcements. The Kavli Prizes celebrate excellence in science and are awarded every 2 years in 3 categories, in the words of Fred Kavli, for the biggest, the smallest, and the most complex. In other words, that is astrophysics, nanoscience, and neuroscience. Each award is a recognition of a significant breakthrough in basic scientific research. So, without further ado, to announce the winners of the 2012 Kavli Prize, it's my great pleasure to introduce the President of the Norwegian Academy of Science and Letters, Professor Niels Christian Stenseth.
Dear ambassadors, dear colleagues and friends of excellence in science, both here at the Academy of Science and Letters in Oslo and at the World Science Festival in New York. Dear Fred Kavli, who I understand is in the audience in New York. Ladies and gentlemen, the Norwegian Academy of Science and Letters awards the Kavli Prize in Astrophysics for 2012 to David Jewett, University of California at Los Angeles, Jane Liu, Massachusetts Institute of Technology, US, and Michael Brown, California Institute of Technology, US, for discovering and characterizing the Kuiper belt and its largest members, work that led to major revision of knowledge about our planetary system. The Kavli Prize in Nanoscience for 2012 is awarded to Millie Dresselhaus, Massachusetts Institute of Technology, US, for her pioneering contribution to the study of phonons, electron-phonon interactions, and thermal transport in nanostructures. The Kavli Prize in Neuroscience for 2012 is awarded to Cornelia Bergman, the Rockefeller University, US. Winfried Benck, Max Planck Institute for Medical Research, Germany, and Anne Graybill, Massachusetts Institute of Technology, US, for elucidating basic neuron mechanisms underlying perception and decision. As I understand, Professor Bergman is attending the World Science Festival in New York. Congratulations, Professor Bergman. Indeed, congratulations to all 7 Kavli Prize winners of 2012. 7 great scientists promoting excellence in science. Thank you very much.
Thank you, Professor Stenstedt, and of course, congratulations to those 7 new laureates. Now, each of the prizes is chosen by an international committee, which is chaired by a member of the Norwegian Academy of Science and Letters. I'd like to invite each one of those chairs to say a few words about why these laureates have been chosen. First of all, the chairman of the Committee for Astrophysics, Professor Oddbjørn Engvold.
In the 1980s, our picture of the solar system was split in an inner part of planets, asteroids, and comets, and an outer region that appeared to be unreasonably empty. The apparent void beyond Neptune, referred to as the Kuiper belt, was challenged and successfully explored by the 3 recipients of the 2012 Kavli Prize in Astrophysics, David Jewitt, Jane Liu, and Michael Brown. David Jewitt and Jane Liu discovered the first of many Kuiper belt objects in 1992. These were then revealed to be small, primitive bodies. More than 70,000 are icy rocks larger than 100 kilometers. Orbiting well outside the giant planet's trajectories, these objects are thought to be fossils left over from the process of planet formation. Michael Brown designed and implemented the Caltech Wide Area Survey, which observed huge area in the plane of the solar system. His program was specifically optimized for spotting the biggest of the Kuiper belt objects, enabling Brown to discover the discovery of Quaoar, Makemake, and Eris. These and many other large Kuiper belt objects made it clear that Pluto was merely one out of many of comparable size. Equally important is Brown's discovery of Sedna, which has an exceptionally large and elongated orbit. With its closest approach to the Sun, more than twice the distance of Neptune, and an orbit that takes more than 10,000 years to complete. The origin of Sedna is a perplexing mystery. 2 fascinating alternatives are that in the early history of the solar system, it was tugged into its current orbit by a passing star, or that it was captured from a different solar system. Equally, all of Jewitt and Liu and Brown's discoveries required creative strategies, a great deal of persistence, and an open-minded approach to expect the unexpected. With cleverly designed observational studies, they have brought fundamentally new insight into the early history and the current state of our solar system.
Thank you, Professor Engvold. Now, from the incredibly large to the incredibly small, next to present the committee's decision for the Kavli Nanoscience Prize, the chair, Professor Arne Skjeltorp.
Nanoscience is the science of the extremely tiny. It involves the study and manipulation of matter at the nanoscale, about 100,000 times less than the width of a human hair. Millie Dresselhaus has done more than most to provide fundamental knowledge in nanoscience on which this new science has flourished. This award honors her specific and pioneering advances in studying the vibrations of carbon atoms, phonons, electron-phonon interactions, and thermal transport in carbon-based nanostructures. She has provided a basis for work on technologies capable of controlling how electrical energy flows. The story of carbon is interwoven with the story of nanoscience. As early as the 1960s, Dresselhaus led one of the very first groups that explored the carbon materials that form the basis for one-dimensional carbon nanotubes and two-dimensional graphene. These early experiments helped to map out the moving patterns of electrons in these materials, critical to further understanding the unique properties they might possess. Dresselhaus revealed an unprecedented microscopic understanding of nanostructures' properties with an exquisite set of experimental techniques. She pioneered Raman spectroscopy as a sensitive tool for characterizing materials that are a single atom thick, carbon nanotubes and graphene. This fundamental research has opened new fields in how thermoelectric materials convert heat energy into electrical signals, or use electrical energy to cool a material. Those that occur in nature have limited efficiency and utility by the strong links between their electrical and thermal conductivity. Dresselhaus improved our understanding of how energy flows and dissipates at the nanoscale and demonstrated that it is possible to separately adjust the electrical and thermal conductivity on carbon nanotubes. Millie Dresselhaus has made pioneering advances in our understanding of electron-phonon interactions on the nanoscale and has helped lay the foundation of the science of carbon-based nanostructures.
Thank you, Professor Sheltorp, and of course not forgetting biology, finally the chairman of the Neuroscience Committee, Professor John Storm Matheson.
This year's Kavli Prize in Neuroscience goes to 3 scientists who in different ways have made discoveries that clarify basic neuronal mechanisms underlying perception and decision. Cornelia Bergman has pioneered the study of how genetic programs control operation of neuronal circuits. She provided the first evidence for the detailed neuronal pathway between a specific sensory receptor protein and behavior. By exploiting the simplicity of the nervous system of the roundworm Caenorhabditis elegans, Bergman has identified fundamental principles of neural circuit logic. The functional circuits of the worm are much like in our brain, but are more amenable to genetic analysis. Winfried Denk has devised 2 experimental innovations of broad impact on studies of how individual neurons respond to synaptic inputs. He developed 2-photon and multiphoton microscopy, which revolutionized high-resolution functional imaging in the living brain. Using this technique, he discovered that direction selectivity is computed locally in individual dendritic branches of so-called starburst amacrine cells in the retina. His other invention of serial block phase scanning electron microscopy then revealed the wiring asymmetry between these interneurons and the retinal ganglion cells that convey motion information to the brain. Anne Graybiel has unraveled the modular architecture of the striatum and discovered striatal plasticity underlying habit learning. A detailed analysis of how multiple cortical striatal loops change when animals learn new skills reveals the way neuronal circuits organize familiar motor patterns into action sequences. The neural loops between cortex and striatum are also important for working memory and cognitive control, and likely contribute to the mechanisms of disorders such as schizophrenia, Parkinson's disease, and even addiction. All of the 3 prize winners have done groundbreaking work on how the brain's nerve connections underlie behavioral reactions to sensory input. Understanding how the brain receives information from the environment and processes it to make decisions is a major challenge in neuroscience. The prize winners have addressed this question successfully in different organisms from worms to primates. They've used a wide range of approaches and have invented new technologies of wide impact.
Well, thank you, Professor Mattisson, and thank you to the 3 chairs and to the judging committees. That is it from Oslo. In New York, I'm handing over to Richard Besser now, where I'm sure you're going to have a great time, particularly Cornelia Bergman. Have a lot of fun at the World Science Festival. From Oslo, we say goodbye to our friends in New York. But most of all, congratulations to the 7 winners of the 2012 Kavli Prizes for their outstanding contributions to excellence in astrophysics, nanoscience, and neuroscience. From the Norwegian Academy of Science and Letters, thank you and goodbye.
Thanks very much, Adam. In Oslo, I want to echo Adam's acknowledgement of our winner here in the audience, and please ask you to stand. Congratulations on your prize declaration. Well, now I think we're all in for a treat as we can dive into some of these fields in a little more depth and understand the work of this year's winners. I want to go ahead and introduce our Kavli Prize panelists who are going to discuss these achievements with me. First is Angela Belcher. She genetically engineers viruses to grow nanoscale structures that can be used in batteries, solar cells, and other clean energy sources. Materials she has developed can also be used to diagnose diseases, and eventually she hopes to power cars. She's the W.M. Keck Professor of Energy at MIT. Please welcome Angela Belcher. Our second panelist is a co-recipient of the 2008 Kavli Prize in Neuroscience. He's made fundamental contributions to neuroscience by revealing the basic principles of how our nervous system communicates, opening the door to strategies for treating diseases like Parkinson's disease and Lou Gehrig's disease. He's Claire Tao Professor in the Department of Neuroscience and Department of Biochemistry and Molecular Biophysics at Columbia University. Please welcome Tom Jessell. And our third panelist is a professor of astronomy and astrophysics at the University of California, Santa Cruz. She studies adaptive optics, a technology that can remove the blurring effects of the Earth's atmosphere and let telescopes on the ground see as clearly as if they were in space. Please welcome Claire Max. So I'll begin with you, Angela. You're a colleague of Millie Dresselhaus. You work in the same field at the same great university, at MIT. When you first heard that she was being awarded this prize, what were you thinking?
Well, of course, I was extremely excited and proud, but I wasn't at all surprised because she's a true pioneer in nanoscience and has been working in the field and making breakthroughs for decades. And as was very well described in the prize announcement, she's just been a true thought leader, an experimental leader in the field. And not only that, she's been a leader in policy and education and leadership for women in science.
She's part of the first cohort of Kavli Prize winners who are women. And yes, this year, three of the prize winners are women. She has a title called the Queen of Carbon.
Yes.
I'd love to have you explain why is she the queen of carbon and what role does carbon play in the story of nanoscience?
So I think that she's called Queen of Carbon because Millie has been working in carbon since the 60s, and she had the great insight to work on these materials before a lot of other groups and a lot of other research were working on them. She started working in graphite and graphene carbon-based materials, and was a pioneer in understanding the electronic properties and structures of these materials. She also worked on carbon fibers, which are really strong, interesting materials as well. And she was able to formulate some of the ideas for predicting that carbon nanotubes were possible before they were actually discovered. And then went on from there to say, well, when you take graphene sheets, single atomic layer sheets, and you roll them in different directions, they're going to have different properties. They're going to be have semiconductors and be metals. And she was able to predict that and then develop techniques and technologies to specifically isolate and figure out the different electronic properties of these individual carbon nanotubes, which is absolutely huge in the field of nanoscience and nanotechnology, because if you're going to use some of these very exciting materials, really understanding their fundamental properties and being able to isolate and understand them is really important.
Now, when she started working in this field, there wasn't a lot of interest there. It wasn't an area that was viewed as very fertile for science. Any insights into why she went that direction and why she persevered?
Well, I mean, knowing Millie, knowing why she persevered it's definitely part of her personality. And reading about, I've learned a lot more about her in the last week or so, and reading about some of her in her biographies. One of her advice to students was to find out what you really love to do and work on it and until you get there, and basically don't let anything stop you. And that's Millie's approach completely. I don't know, and I know that she was one of the first people to think about these materials as being very valuable materials and approach them in a very rigorous scientific way. But I've also learned that I'm definitely going to follow what Millie does, because she seems to always be on the right track.
Turning a little bit to your own work, Richard Feynman declared in a famous speech, "We must learn to make things atom by atom." Now, how does that apply to the work that you do?
So the work that I do is trying to interface biology and nanoscience and nanotechnology. And biology already gives you this incredible toolkit of molecular scale and nanoscale objects, protein and DNA, antibodies that are already on the nanoscale. And what we've done over the last 10 years was try to convince organisms to work with materials on the periodic table through evolution they haven't had the opportunity to work with, and see if we can bring together the ability of biology at the nanoscale to control materials at the nanoscale, to give new properties to materials, and to give a genetic code so that a material can be made in a very tailored way by biology. So to give a genetic sequence to a material that's not biological and that normally wouldn't have a genetic sequence.
All right. For someone who is just trying to understand a little bit about nanotechnology, what application might this have for the world in which we live, for diseases, for energy?
Well, nanoscience and nanotechnology in general is being able to understand or control atoms and placements of atoms and orientations. And that has so many different possible applications. That has applications in energy. It has applications in the environment, applications in medicine, of which you've heard about and mentioned earlier today. And what we work on are controlling the placement of atoms and collections of how atoms come together for solar energy applications, to try to more efficiently collect electrons. And we use some of the same materials that Millie has worked on to convince viruses to grab onto them and arrange them in particular locations to better collect electrons in devices. And we do it in batteries, and we do it in detection of tiny tumors.
Fantastic. Thank you very much. Let's move on to our second prize area, which is neuroscience. And Tom, when hearing briefly about those winners, it wasn't clear to me how they all pulled together. Why this group of winners, and how does their work relate to each other?
So when I heard this announcement, beyond the initial feeling of sort of excitement, because each of the recipients is a very accomplished, distinguished scientist in their own right. There are two things that struck me about the sort of common bond between Corey, Winfried, and Anne. And one is the idea that what they've been doing over the last decade or two is really sort of placing a premium and an attention to the organization of circuits and the anatomy of the nervous system, and using that information to, through the clever application and creation of technology, to understand aspects about neural function and its links to behavior in a remarkably creative way. And the second is this general idea, I think, of their science sort of characterizes the process of invention and reinvention. And by that I mean that each of them have worked in fields that have become part of the central canon of neuroscience, but through their efforts, they've changed the way that we think about either the utility or the function of an organism or a particular part of the brain. Maybe I can explain that a little bit. So let's start with Corey, since she's sitting over there. You know, so when I think of Corey, and I don't want to get too ponderous here, but you know, if Churchill was around, maybe he would try and describe Corey's work as in the way that, you know, never before in the field of neuroscience has so much been revealed to so many by an organism with so few neurons. Corey has taken the nematode worm, and which was introduced by Sidney Brenner and by John Sulston and John White, and they gave us a preliminary wiring diagram that in principle was supposed to reveal the way that the brain functioned or the nervous system functioned. And Corey single-handedly has turned that wiring diagram into a sophisticated understanding of sensory perception, the way that the sensory inputs control behavior. And she's done that in a way that has not confined itself to a simple invertebrate organism, but she's dealt in a context and a dialogue that is the stuff of mammalian, primate, human neuroscience. And she's revealed aspects of nervous system function, too numerous to detail here, in a way that sort of defies belief that a nervous system with 300 neurons could perform in a sophisticated a way. And much of that has come through the creative use of new technologies to map synaptic connections, to map the function of neurons. So this is a single-handed tour de force in an organism that basically is remedial. And so, yeah. So Corey's Winfried, I don't know whether you've read this book, The Eighth Day of Creation by Horace Freeman Judson, which is arguably one of the most sort of insightful accounts of the origins of molecular biology and its impact on the world. And when you read that book, you realize how difficult it is to switch fields. The idea that physicists became molecular biologists and molecular biologists became neurobiologists, that's a hard thing to do. And Winfried Denk trained as a physicist and yet has had an enormous impact on understanding and insight into neural science by the clever application of basic physical laws. So the first thing that Winfried did is sort of take conventional light level microscopy to a new stage with the invention of a 2-photon microscope, which he did as a graduate student with Watt Webb, so that's not too bad as an initial. And what that allowed you to do is to probe and look deeper into the nervous system and into the functional nervous system by combining this with methods of calcium imaging, and gave experimentalists new insight into the dynamics of the nervous system as it was actually thinking and acting. And this was all the clever understanding and application of the physical laws of optics in combination with something that would be effective for biology. And then more recently, Winfried has, again, gone back to this idea of neural circuitry. The worm, we know the wiring diagram. The mammalian brain, we don't have the faintest idea of the functional wiring diagram. And Winfried and others have taken it upon themselves to remedy that situation. And Winfried developed this clever method for serial EM reconstruction of nervous systems that in some ways galvanized the field and has generated a new scientific discipline, which some people call connectomics, and is in parallel with the sort of idea of genome sequencing, if you could map the entire pattern of connectivity of the nervous system, would we gain new insights into how the nervous system functions? So Winfried is characterized by this constant state of reinvention of methods and ideas and the rigorous application of this. Anne Graybill. Anne comes from a different discipline, more in the range of sort of traditional psychology application to nervous system rather than physics and genetics. But what she did in the 1980s is popularize the idea of the matrix some 15 to 20 years before Keanu Reeves reintroduced this. And what Anne did is demonstrate that in a region of the nervous system that we're familiar with, the basal ganglia, there is an organization of patch and matrix and striosome that no one had appreciated before, that revealed the topographic organization of connections in this region, which was itself a dramatic observation. But in addition, what she has done is, I think, overturned the conventional view that the basal ganglia is good for only one thing, which is just the simple, important control of movement, and has revealed that the basal ganglia is a much more rich and subtle region of the nervous system that is involved in, if you like, the habitual brain, the way that motor patterns are pieced together serially, the idea that there is dynamic change, a trial and error learning. So Anne's work, through a sort of clever combination of anatomy and behavior, has completely changed the way that we think about a large central region of the nervous system through this clever application of physiology and anatomy. So all three, I think, recipients here share this common feature of taking an existing field and turning it on its head through this clever application of anatomy and technology.
One of the areas that I think is fascinating is how this applies to decisions we make. How will understanding the neural pathway from the point of sensation through to the brain help us understand how we make decisions?
Yeah. So much of neuroscience, I think, I mean, in a sense, all of neuroscience is trying to understand how sensory information in the world that surrounds us leads to directed behavior, which is achieved through movement. And so much of the field traditionally is concentrated on the nature of the sensory input, how the organism processes the vast array of sensory information that it's exposed to, and how it moves, how the nervous system controls muscles. But Vernon Mountcastle, one of the early heroes of the field, defined the important aspect of that transfer of information from sensory input to motor output as the big in-between. And in a sense, this big in-between is this process of decision-making. How do you take all of this sensory information and in a judicious way select those bits of the information that are relevant to a particular behavior and transfer the reference frame from sensory to action coordinates? And decision-making is all about that. And it's a tough thing to study because it's right in the middle of the brain. So you're far away from the sensory world, you're far away from the muscle world of movement, and much of the interest in this field is focused on that big in-between region. And Corey's work is beginning now to get to grips with the process of actually integration of sensory input and transfer to motor output. Winfried's work, I think, is sort of more still at the sensory level, and Anne's work is very much in this big in-between area of how this region, the basal ganglia, actually selects information and assigns it, refines it for particular movements. So this is the future of the field in many ways.
Let's talk a little bit about the technologies and approaches that these researchers have taken. And the impact of that on strategies for dealing with diseases like Parkinson's or Huntington's or even drug addiction. What's the application?
Yeah, so I think Martin Rees, the president of the Royal Society, once said that there are two types of research and only two types of research. There's applied research and not yet applied research. And so neuroscience is very much the not yet applied research with the intent of application. And Anne's work in understanding how the basal ganglia controls movement is absolutely central to an understanding of disorders like Parkinson's disease. it's slightly embarrassing, I think, that with the great fanfare of neuroscience in the last 20 to 30 years, one of the few interventions that actually has improved the human condition is deep brain stimulation in Parkinson's disease. That in part is based on a rather profound understanding of the organization of basal ganglia circuits, but we need to understand more. We need to understand the basic logic by which that region of the nervous system controls action selection. And if we could understand that, then we would understand much more about how to intervene. And in a funny way, Corey's work, even though it's done in this remedial creature, is revealing details of this transformation that may have direct relevance to understanding human control of movement. And Winfried is providing a basic set of technologies that are going to drive and empower the field in any region. So Winfried is this fundamentalist who's trying to give us methodologies that allow us to approach any problem, whether it be in movement or cognition or whatever you like to look at.
Wonderful. Thanks very much. I want to move on to you, Claire, to talk about astrophysics. And can you talk about how the work of these laureates has changed what we know about how our solar system got here?
Well, first let me say what we know about our solar system, period.
Yes.
Because until 1992, when Jewett and Liu discovered these very small icy objects out beyond the orbit of Neptune, there was basically thought to be nothing beyond the orbit of Neptune except for Pluto. And now we think there are 70,000 or so of planetesimals that are made up of the stuff that the solar system was made of and that haven't been processed like the Earth has been processed. So we can actually figure out where we came from in the protoplanetary disk. And actually there's a spacecraft that NASA has launched called New Horizons, which will first fly by Pluto and then fly by one of these objects, or maybe even 2 or 3 of these objects. And to put in a plug, the choice of which objects they're going to fly by that, in this vast belt of 70,000 is up for grabs, and there's an open website where you can go and you can help choose which objects this spacecraft will go to.
Do you offhand know that website?
I don't remember. Type website, New Horizons.
All right, we'll get that information out to you. I'll tweet that out. You can follow me on Twitter. I'll send that out. Yeah.
The second thing that's now getting to the other part of your question is where does the solar system come from? How was it made? That has really come into question based on the discovery of on the order of 1,000 or more other solar systems with other extrasolar planets, where it's clear that they don't look anything like our solar system. And before extrasolar planets were discovered, we had a great theory for how the solar system got here, and it produced our solar system. It didn't produce any of the other solar systems that we found. It's thought that these other solar systems, their evolution was dominated by planets migrating in and out, closer to their star, farther from their star. And yet, it's not clear that there was much migration at all in our solar system, and if there was, how we access it to figure out what happened. Well, one of the main ways to understand the structure of these 70,000 objects that Jewett and Liu and Brown discovered has to do with Neptune migrating in and out in response to Jupiter's migrations, producing the distribution of velocities in this cloud of 70,000 objects. So finally, we have a grip on what might have happened in our solar system in the very early days. Very chaotic. One of the most interesting papers in this area is called The Wild Days of Neptune by one of Mike Brown's former students, I believe. So there was a lot going on in the early solar system that we don't understand, and this is a real way to figure out what's happening. Finally, Sedna, which is this crazy object whose orbit is way outside what anybody considered was possible and loops outside the previously known bounds of the solar system, is so extreme that you have to really think out of the box in order to figure out how it got there. And as the video mentioned it might have been captured from another passing solar system. There's a thought. We can get our hands on something that came from someplace way far away. But also, it might have been perturbed into its current orbit in the cluster of stars that our solar system originally formed in. The sun was born in a cluster of stars, as are most stars. And we can actually figure out what the properties of that stellar cluster must have been in order to have made Sedna. So we're getting way back, more than 4 billion years ago, into how our solar system got here by looking at these objects.
So is this a big insight, what we're hearing today? I mean, the work of these researchers?
I think so. We thought so on the nominating committee, absolutely.
Well, talk a little bit about that. So you were on the nominating committee.
Yes.
How was that experience?
It was really interesting. It was stimulating, fun, challenging. The process, you may not know, the process is to solicit nominations from every place, sent in to a central website, of course, with a lot of material associated with each one. And there are a tremendous number of fantastic people to choose from, and it was very, very challenging to figure out, of all these good people, which ones were suitable for the Kavli Prize. The spirit of it and the aims of the Kavli Prize as an institution. What I enjoyed the most about it was actually digging down in the literature and getting to read what these candidate prize winners had written and really understand, or try to understand, how they had gotten to where they had gotten. It was an international group, very collegial. I was very impressed with how the whole thing ran.
So why is it important to understand what made up the early solar system?
I think we all want to know where we came from. And cosmology deals with how the universe started 13 billion years ago, and how the solar system got here has been much more thrown into question since the discovery of all these other solar systems. How does our solar system, which doesn't look like any of them, fit in? And getting a handle on what happened 4 billion years ago is to me, pretty exciting. I think.
In terms of understanding and the advances that have been made, how has technology contributed to that?
That's a great question. So both Jewett and Lou in the early 90s and Mike Brown and his colleagues in the early 2000s started out using technology that didn't work. So to find very faint objects very far away, you have to survey very large fractions of the sky in order to find these rare and not very easy to detect objects. And they started out using existing telescopes, but with photographic plates that are this big and that have to be developed and so forth. And both groups didn't find anything for many years. They had these very thoughtfully laid out schemes for how to find what they were looking for. And they didn't find anything. It was only when CCDs came along, the same device that you have in your cell phone.
What is a CCD?
What is a CCD? It's an electronic device that detects photons, little bits of light, very, very sensitively.
Okay.
And it was the sensitivity that let them really finally see these faint objects. These are big cameras. The CCD in your phone is this big. The cameras that are now being used have 1 billion pixels, and you can hug them. They're this big. So this is a huge sea change in the last 20 years for how to detect them.
I mean, in reading about their work, they took these photos for years without finding anything.
That's right.
Who is supporting that research?
I honestly don't know. I imagine it was the National Science Foundation, but I don't know.
What are some of the big technological challenges that you're facing right now in the field? What are you looking for in terms of the next advances?
Well, I'll use your question to talk about the technological challenge that I'm most involved with, which is called adaptive optics. So for telescopes on the ground, which you can build really big, because they're heavy and you can make them as large as you can conceive of, turbulence in the air really ruins the quality of an image that's coming from outer space. And so what adaptive optics does is it measures the turbulence hundreds of times a second, and then has a mirror behind the big mirror of a telescope that changes its shape and corrects for the blurring effects of the turbulence. So you can see objects as clearly on the ground as if you would see them in space, which is actually being applied in this area because people have used adaptive optics to detect satellites to these, to the brightest ones of these objects that are beyond the orbit of Neptune. And when you have a satellite going around an object of unknown mass, you can use the orbit of the satellite to figure out what the mass of the object is. Just like you can measure the mass of the sun by looking at the orbits of the planets.
Fantastic. Corey, would you be willing to take a question? We have a hand mic. Now, we've heard your organism being disparaged up here. What led you to pick this organism to study, and what can we learn from a worm?
So first of all, the worms are our partners and our collaborators. And the reason that this has become an exciting organism for neuroscience is the fact that you can really try to understand the whole nervous system at once. That what Tom described as the big in-between is a lot smaller in-between from point A to point B, so that you can actually try to understand the complete set of calculations that are taking place on the way from point A to point B. That's something you can attempt to think about when you're thinking about 300 neurons, but not when you're thinking about many billions of neurons in our own brain, at least not yet. So it's the appeal of that. It's the appeal of being able to relate function to anatomy, to physical reality, and then to the behavior of a whole organism, moving vertically from to understand all of these levels that makes the worm attractive. It sort of opens itself up to us and lets us see what's going on. Literally, in the sense that it's transparent and you can see right through it. You can see everything that's going on in the worm's brain while it's thinking.
And what have you learned from there that can apply to humans?
I think one of the important things we learned is that the brain has pathways that are innate that link certain kinds of signals to certain kinds of behaviors, that we have instinctive pathways that trace through the anatomy of the brain that can help us to make the right decision the first time we encounter something, which does not preclude learning about it, modifying that experience later on, but gives you a sense of a pre-pattern or organization for behavior. Now, this idea might not seem that surprising to you, that there would be fixed sorts of pathways, pre-patterns, in an animal as simple as a worm. But Charles Zucker, who's here in the room, has shown that the same idea applies to the sense of taste and smell in mammals as well. That children are born knowing that they like sweet things and they want to reject bitter things because of these kinds of pre-pathways that are set up to give you the right behavior the first time.
Fantastic. Thanks so much. I have a question from the internet for any of you or all of you. And it's this: science literacy seems to be at an all-time low in the US, yet scientific research is very strong. How can you account for that discrepancy? So an easy question from the internet.
The answer is clear. We do a poor job of communicating the intrigue and interest and excitement of science at a stage when kids are still malleable and receptive, I think, as one looks at, elementary schools, middle schools, high schools.
What got each of you excited about a career in science when there were so many other things to think about doing?
I can start out. When I was 8 years old, I went to a summer camp, and there was a counselor that had a little telescope, and he pointed it at the moon. And those of you who have looked through a little telescope at the moon, you can see mountains that are just obviously mountains with a telescope that is not fancy at all. And it just clicked that the mountains on the moon must be just like the mountains on Earth. And I had a personal relationship with them. And I've wanted to be an astronomer ever since.
Fantastic. Angela?
I also got very interested in science at age 8. I fell in love with DNA and genetics when I was very young. And I knew that I wanted to be an inventor at the same time.
How were you even exposed to that at age 8?
Yeah, I'm not exactly sure. I think that some of it was in school, and other was through interactions that I had with other adults that were in science. And I thought that being an inventor was a very important job, and so I spent a lot of time in my garage growing up trying to figure out what I could invent that would be useful for the world. And I didn't have any success stories really until later on. But to me it was very innate, and I think that's very common in children in general. That I do a lot of teaching in elementary school of science and engineering, and the kids want to learn more and more, and so I think that it's a matter of nurturing that. And I also agree completely that it's a communication. And I was impressed with my colleagues here today how well they communicated their fields, and so I think we need more focus on that.
Tom, you grew up in a different system.
I wanted to be an art historian, but it's important to know one's own limitations. So dug around for something else to do.
Yeah. Well, I think that John Holdren was talking about that as well, the importance of stories and making it all real, so that it isn't something that's just abstract, but it's something that you can relate to. And we have another question in on Twitter using new technology. All right, this one is for you on astrophysics. What difference does it make to the world if we knew where we came from?
I think it gives us some humility and some perspective that the human race has been around for some tens of thousands, and on the top end, a large fraction of 1 million years, and we're learning about stuff that's 4 billion years ago, and it's sort of, I'm a little bit tongue-tied about this.
Yeah.
What I can say, what I get out of it is this sense of perspective, and I think also being a steward of the Earth and the Earth's resources, given the fact that the Earth has been around for 4 billion years, and we'd like it to stay flourishing for at least that much more time.
Yeah. And then one last question for you all, having to do with prizes. And what is the value of prizes like this for people who work in fundamental basic science? Is it a motivator? Is it something that encourages people in the field, or is it just a momentary pat on the back?
I'm not sure if it's. I think that people that are working at this level, that they get prizes, they're not using the prizes as a motivation. It's more that they're doing what they absolutely love. And my thought has always been is if you find out what you absolutely love and go as fast and far in it, then that's a great motivator. And I think what's impressive about looking at the prize winners today is just the role model that they do set for kids, because it was described as being heroes, and these people are heroes in science. And it just when I was learning more about Millie in nanoscience, I thought she's my hero also, and it made me want to be better and made me want to work in the same areas that she's working in. And so I think it's a huge motivator for future generations.
I would say that one of the virtues of this sort of prize is that it actually provides a recognition of the field as a whole, and that it provides enthusiasm for young people to get a sense that people are paying attention to what they're doing. And it also points out that, I mean, one of the things to recognize about such prizes is that they tend to place undue focus on the individual, not that the individuals aren't deserving, but in most cases these are team efforts, and the prizes are awarded in recognition for 10 or 20 years of collective effort, at least in the biological sciences. And so what these forms of recognition do, I think, is provide encouragement and enthusiasm for a group of people who've been contributing to a larger effort. And while focusing on perhaps one or two individuals in that field. So to me, it's a recognition of the field as well as the individual.
Clay?
Yeah, I think when I started serving on the committee, the criterion was for a discovery, and I originally felt like, well, gee, I don't want to just reward somebody who got out of bed one morning and happened on accident to discover something. But it turns out, as you were saying, that these things were products of 5, 10, 15 years worth of very concerted effort with very goal-oriented people. And I ended up feeling that even though the naive interpretation of the word discovery is more, something that happens quickly, I felt very comfortable rewarding people who had in fact been working for a long time, and it's essentially rewarding a whole decade or so or more of effort that turned out really well.
Well, this has been a wonderful morning hearing about all of the prize winners and their tremendous research. Let's have a round of applause for our panelists. I want to thank the Kavli Foundation for sponsoring these awards and the World Science Foundation for having this session. I hope you all will be attending more of the World Science Foundation program over the weekend. It's a great way to get kids excited about science and adults as well. So thanks very much, and thanks for coming.